Hello and welcome to this webinar this morning with me, Miles Brining, regarding simulation 2D. Okay, so basically the 2D side of thing is something that's added into SolidWorks Simulation Professional. Alright, so I'm going to show you some examples today of exactly how it works. So if I just go ahead and let's just shoot straight into SolidWorks. And to bear with me, I'm just going to go to meeting software out the way. Right, okay, so what I'm going to do in this is just show you some example of a standard study, and then I'll run it through in 2D and we'll compare the differences, alright? So first thing I'm going to do is just go to the simulation tab, alright, or the menu up here, and then go to study. And I'm just going to set a new static study to self first. So I say this part is very simple. It's overly simple, to be honest, but it does the job. So I'm just going to go ahead and set this up. So let's put a fixture up here, and then I'm going to put a load. So let's say a force, and we'll put it onto this face here, going in the downward direction. So I'll just go and set that up here, and let's say this is going to be 100 newtons. Right, so. Okay, next thing I'm going to do is I'm going to go and mesh it. So if I just create a mesh for it, hang on one second, just make sure my loading is actually going the right way, which it isn't. Be careful there. That's better. Right, if I go ahead and mesh it now, and we'll put it on a curvature based mesh, and let's put it on the finest on the slider, which is the largest element size is about 2.3 millimeters. Just go ahead and mesh it. Alright, it was fairly quick. Alright, if I go ahead and run this, let's just see how long it takes. So it's about 7 seconds. Alright, I think the mesh was roughly the same amount of time as well. So you can see here that the maximum stress in this, on this von Mises stress plot, is about 11 and a bit MPa. Alright, so it's fairly low for the amount of force that I put on it. What I'm going to do now is I'm going to replicate this in a 2D study, and we'll just compare the speeds of it. Alright, so again, this is very simple, so it didn't take very long to solve at all. But you can imagine if this bracket was much longer, the difference between this and a 2D study would be quite a bit different. Now, obviously, the more geometry in it, the more it compounds as you add more and more stuff on compared to a 2D study. So, as I said, a 2D study, simplification studies, as it's called, is available if you have Simulation Professional. If I go to the Simulation Study menu, and then I go and put it on static again, and this time let's use 2D simplification, which is this tick box down here. And then go OK, and you can use this on additional testing. It doesn't just not just for static, the 2D simplification. Obviously, it does have to follow certain rules, so you do have to have some sort of symmetry involved in your model. If you don't, then you're either looking at it from a specific area of point of interest, all right, or it's circular, all right. In which case, that's again, that's fine. So if I go ahead and put it on static and then green tick it. Alright, so I've got a number of options here. So I've got plane stress, I've got plane strain, and then I've got actually symmetric. Okay, so this one here, the plane stress, is used when your model is very long and very thin. Alright, so you can see here I've got a spanner, and then the force is being applied and the fixture, and it's just bent down, and you can see because it's very thin, that's fine to use. It just gives you a nice example here and what it should be used for if you forget this. Just bear in mind that everything that I'm doing regarding a 2D simplification, it won't work with anything that's normal, any forces that are normal to the section plane, so what I'm actually cutting it with. So just bear that in mind. Your 2D simplification may not be the correct type of study to do. If I do have loadings, I'm going to slice it down the middle here, you see. So if I have any loadings going in this direction, Alright, so in the Z direction, in this case, it wouldn't work. So the plane I'm going to use is one of the planes in here. So let's use the front plane. So you see here then it's cut the actual model. The section depth is important. Alright, so for instance, I know the model thickness on this is 30 mil. If I was to put 10 mil in here, the forces that will come out on the plot will be 3 times greater than if I was to put 30 on here. Alright, so 30 is the actual depth of the model. Okay, so it's important that you do get this right. Either that or use a pressure. Alright, so if you're using forces, make sure this is right. If you're using a pressure force instead of just a normal force, this doesn't matter. Alright, so if I go OK on that, just to explain the other ones. Alright, actually I'll come back to that in a minute. Let's just go ahead and do this. So if I green tick it, so you can see here I've just got a infinitely thin cross section of my model now, and then I can go ahead and then add some fixed geometry to it. So I can fix that there, and then let's put a force on, let's say, this face here, and let's do a selected direction. So it's already selected the front plane for me, which is quite nice. Let's make sure that the force is going in the right direction. So we're going downwards on this edge, and then I'm going to go ahead and mesh it, and I'm going to mesh it on the curvature based mesh again on the finest setting on the slider, which is about 1.1 mil on the largest element size. And you can see that's very quick. That took less than a second to do all that. Alright, so let's say this is a very simple model, and you can see the difference. It was at least 6 or 7 times faster than doing my solid mesh and meshing it. In running it, if I go ahead and run it now, very quick again, and you can see from here it's about 12 MPa. Alright, so if I go and compare that to my first study, it's 11.3. So you can see very close. Alright, and it took hardly any time to do it at all. So what you can do with this is obviously maybe run a 2D first. You may find that the stresses that are going through the model at that point are so low, there's no point running the 3D study, you know, the standard static study in this case. And because of that, you might be happy to leave it at that and say, look, this is the stress in this area. If not, you can always run a normal study after that and just refine it even more. Obviously it takes longer to do that, but you'll get a more accurate result. Okay, so if I show the stress test here, alright, so the plot, as I say, it's 12. You can actually show this as a 3D plot. Alright, so it's slightly easier. You can see it is all uniform. Alright, so it is just a render of my section. Okay, but let's say that the section depth is important. So if I was to put it to 10, this would be in the 30s. Okay, so it'd be about 34, 36 MPa. Alright, so it is important that you get that right. Okay, so let's just go back to the model again. I've got another configuration here, which is a long bracket, which is this one here. And if I was to go and do another study on this, and I do a static study, use the 2D simplification again, and then green tick it. This is an example where you would use this one, so the plane strain. So we could say that's the plane there, and then the depth, let's say it's 300, go OK, and then I would repeat the process on this, and I would get a more accurate result using it that way. Okay, so just remember, if I go back, if it's really long like this, and then you're doing a section through it like that, use the strain type of measurement, so the plane strain. If you're using a very slender model like this, okay, then use the plane stress approach. Okay, I'm going to show you one more type now. So let's just minimize that, and let's go back into this model here. So I've got a flex bellow here. So I'll let you decide what it's used in. Let's say it's used in an exhaust system or something like that. Alright, so this exhaust gas is going through this, and it does move, alright, so it does compress, and also there is a fair amount of heat going through it. Let's say there's 150 degrees Celsius running through the center of this tube. So someone has given me this and they've asked, can you just tell me with 150 degrees of heat going through it and with a certain amount of force either from the exhaust pipe, either end of it compressing, for instance, whether it can withstand that force. So what I'm going to do is, first off, I'm just going to run a new study, and I'm going to do all of this using the 2D simplification method. So I'm going to do a static study first. Let's just do the thermal loading first. Let's get that out of the way. So again, thermal loading is something that you can apply in either static, which is just a constant temperature, all right, or you can do a thermal, which is almost like a transient thermal study over time. What I'm going to do is I'm going to do it as a thermal load in this instance, just to mix things up a bit. And I'm going to use 2D simplification on that, just to show you how you can use it on the different items in this list. And if I go OK, so again I'm going to do an axisymmetric type of 2D simplification, and I'm going to select, let's say, the right plane, split it, and it does need an axis of symmetry. So if I do that one there, you can see it's then picked the actual side of it, which is good. I can go OK. This model does actually have three bodies. So we have what's called, these are V-band clamps. So there's one on this end, there's another one on this end, and then there's the actual flex. And for this study, we've considered that the V-band and the flex have actually been welded together permanently. All right, so it's bonded. I'm going to have a bonded condition. All right, which means that this is glued to that, and this is also glued to that. So for this example, it is almost like one hole. Okay, so thermal load. Let's put a temperature on it, and let's say that the temperature is going to be on these faces here. So it's going to be on the inside face. So if I do select tangency on this one here, it'll do all the inside faces for me. And then let's say that the temperature in Celsius is going to be 150 degrees. All right. You do get this kind of weird preview on half of it sometimes. It's just a quirk in the system, unfortunately. But you can see here that it has actually applied it to that entire bottom edge, so the inside of my flex, which is fine. I'm going to go ahead and mesh it now, and because obviously I'm using 2D simplification, I can really crank up the fineness of the mesh. So let's do something like that. Okay, so it's very fine. You can see here I've got lots of elements going from the inside to the outside of the material. Okay, the general rule is that you have at least two. I've got at least 5 or 6 there in some instances, which is good. And also I'm just going to go right click and go properties on this thermal study, and I'm going to make sure that the initial temperature is, well, first off I'm on a steady state, and I think that's one thing I need to do in there. That's fine. That looks good. I'm going to use a direct sparse solver in this case, and I'm going to go ahead and then just run this now. So alright, it helps if I put material on it as well. So let's say this is going to be using 304 stainless. Alright, and if I just run it now. Okay, so the thermal loading is now being applied to it. Okay, what I can now do is I can go ahead and then apply this thermal loading into a static study. So if I go ahead and start a new study, and I'm going to go and just start a static study using 2D simplification again, and then I'm going to select my right plane again on axial loading, and I'm going to select that one there. There we go. You do have the option to select the other side here, alright, if you need to, if it's not quite symmetric. You may want to set one side or on the other. That would be an example, for instance, if you had a lug on the end of it or something, which you weren't You wanted to apply force through it, but weren't too interested in everything else. So what I could do is now is apply a fixture to this. So let's do fixed geometry on, let's say, this end, like that. And on the other end, let's just say I'm going to actually let's do our thermal loadings first. So if I edit this, I'm going to put it on roller slider. So this means it can move up, upwards and downwards, but not in and out. So we're saying that the pipe on each end is stationary, but the heat has been applied through this flex bellow, and I want to see exactly what kind of stresses are going to be applied just from the thermal loading. So if I go ahead and go to the properties of the static study, and in here if I go to the flow thermal effects section here, I can do thermal study 1 there as the one, and let's say the room temperature is say 24 degrees, okay. And then from that I'm just going to go ahead and also mesh it. So let's just create a, say, a very fine mesh for this, like so. And then I'm just going to run it now. Okay, again, I need to apply the material. So you can never run a study without a material applied. Let's just do 304 again, and then just run it. Very quick. All right, it doesn't take long to do these, which is good. With that amount of thermal loading, it's very close to yield. All right, it doesn't necessarily mean it's going to be a bad thing. You may find after it's been through a few heat cycles, these stresses would come down, but it's definitely going to displace it a certain amount. What you can do is when you get these 2D studies, as I said before, once you actually click on the plot and have it activated, you can right click and go show as a 3D plot, and it does a nice 3D plot and then leaves you a nice section on one side. So you can see here it looks almost identical to the, well, it is identical to the initial geometry we started with. So if I go ahead and animate this now, okay, so it's fairly quick there. Let's make that slightly more, so let's say 20 frames per second, just slow it down a bit. So it gives us a nice understanding. I'll say this is exaggerated by a certain amount, alright, probably by a factor of about 30 or 40 as a guess. Let me just run that again, hang on. So let's say 30, let's just do 20, I don't want to take it too long. And you can see now that it's running through frames, so almost there, it's frame 15. That's 20. There we go. So you can see exactly how that temperature would affect it. Alright. As I say, it is exaggerated. Let's see exactly how much it's exaggerated by. 118 times, so I was way off. Okay, but it's quite a bit. So it's no way you can see it's almost touching here. It won't do that. All right, it exaggerates all of it, but it gives you a good understanding to see exactly how it will move. Okay, so that's how you can apply a thermal load from another 2D simplification into this. Maybe then I can do another static study, and in this one, let's say that the again use 2D simplification, and I'm going to select the right plane this type, and make sure it's on actually symmetric. Do that again, and this time let's do a force on, actually let's do it as a pressure just to make it a bit different. Let's say we've got the pressure on this face here of, let's say, 1 MPa, that's fine. And remember, if you need to work out the forces, if you are using pressures on the end, if you do use a pressure, it's a total area, it's the force divided by the total area will give you a pressure. If I go and do a fixture now, let's fix it on this edge here, and then go OK, and my force I just make sure it's going the right way. It's better. Okay. Now what I'm going to do is just mesh it again. So let's do it on curvature on the maximum on the scale here. And if I run it again, I'll do this every time. Let's run it on 304. Very quick. Alright, and again if I animate this, so show it as a 3D plot and then animate, you can see exactly how it works. There we go. Actually, you can build up a nice example of that. And I could take this a step further. I could do another study where, for instance, if I go back to this one, I induce a force onto the side of this as well as the heat and see whether it can withstand it. And so you can add to this thermal loading. You don't just have to have a static with a thermal load on it on its own. All right. Just a few tips on that as well. If you were to do that, with thermal loads, if I was to apply it on this and this was a fixed end, so I wasn't using roller slider, I'll end up with some very large stress concentrations on these corners. Alright, because it's trying to expand and this is saying under no circumstances move. So you produce, just remember you tend to end up with inaccurate or singularities round fixtures if you don't set them up right, because obviously we are making assumptions on how this is moving. Okay. Right, so hopefully that's been a nice introduction to the 2D simplification feature within Simulation Professional. All right. If you do have any other questions, then feel free to get in contact with us. I'll shoot up our details now for you. There we go. So you can either get in contact with us via our email address down here. We do have a number of upcoming webinars. All right, so we have in context modeling next week, and then after that we have the week after that we have it on sim submodeling. Okay, thanks for watching. Hope you've enjoyed this.